Hello everyone, welcome back. So we have discussed the issue with respect to the closed system for the carbonate equilibrium, right? So we have carbonate as in H2CO3, HCO3 minus and CO3 2 minus, and we looked at what were the relevant equilibrium concentrations going to be if you added the relevant compounds, right, initially. And we also looked at how to use Vimintek in that particular scenario. And today we are going to move on to the much more complex system where it's going to be an open system. And what's the difference here? So earlier it was not open to the atmosphere, but now let's say your three particular species, right, H2CO3, HCO3 minus and CO3 2 minus are open to the atmosphere. So while HCO3 minus and CO3 2 minus by themselves, do not change phase, H2CO3, as you know, right, is going to stay in equilibrium with carbon dioxide in the aqueous phase, and this carbon dioxide will equilibrate with the open system now, right. So let's see what that is. Let me try to represent that in a better manner. So here we have, let's say, right, this is water and this is atmosphere here. So let's say initially I have no carbon dioxide in the water or no carbonate system in the water, I have nothing there initially, and then let me say that I have 5 moles of CO2 here initially in the atmosphere, right, and after equilibrium. So this is initially, and after equilibrium has been achieved, let's say, what's it going to be? I mean, I guess we need to look at the relevant Henry's constant or such, but now let's say there might only be 2 moles in the atmosphere and 3 moles now in the water. We are talking. So what's happening here? The carbon dioxide is changing phase from the gaseous phase to the aqueous phase, and this particular CO2 in the aqueous phase can further be or will further be in equilibrium with H2CO3, and which will further be in equilibrium with HCO3 minus and H plus, which will again further be in equilibrium with CO3 2 minus and H plus, right. So what happens to your system now? If you had no moles of carbon dioxide in your aqueous phase or in the water, and if you had some moles of carbon dioxide in the gaseous phase, so you are going to have carbon dioxide entering the system, and then your carbonate system, or H2CO3, HCO3 minus and CO3 2 minus being formed, and also consequently or simultaneously bringing down the pH. So let's look at the inverse case. What can happen here? So let's say I have water here initially, right, and I have 5 moles, let's say, of carbon dioxide, and there is no carbon dioxide in my atmosphere here, right. So for example, assume that this is a 1 liter container and it is 0.5 liters of water and 0.5 liters of air that has, or atmosphere or air, I guess, that has no carbon dioxide in it. So after equilibrium has been achieved, what's going to happen now? So this is the case similar to what we looked at just earlier when the carbon dioxide moved from the gaseous phase to the aqueous phase, but now we have the inverse, where that we have some moles of carbon dioxide in the aqueous phase and none in the gaseous phase, right. So now you are going to have a transfer of carbon dioxide via the H2CO3 to CO2 aqueous to CO2 gaseous, right. So what's going to happen, let's say, or what can happen is that after some particular time the equilibrium will be achieved, and now let's say there are only going to be 3 moles of carbon dioxide here and 2 moles of your carbon dioxide in the gaseous phase, and these 3 moles, and what forms will they be? They will be in either CO2 dissolved or aqueous form, which will be in equilibrium with H2CO3, which will be in equilibrium with HCO3 minus, which will be in equilibrium with CO3 2 minus, right. So it's a fine balance now, right. You choose, or let's say you try to vary any of these variables, it's going to affect all the other variables here, right. So it's like a balance now, right. Somebody walking a tightrope now, right. You push it some way, it's also going to affect all the other aspects or the variables. So for this particular system, now we are going to analyze how to go about it, right. So it's a complex case, so let's go through that step by step, I guess, right. So again, component balance. So again, component balance, right, and we need to now list the species. So we are going to first list all the species that are going to be present in the aqueous phase H2CO3. So when we write H2CO3, it more or less means we are also referring to carbon dioxide in the aqueous phase, and HCO3 minus and CO3 2 minus, and then OH minus and H plus, right? And let's say in this particular example too, we are adding NaHCO3 and Na2CO3, right? And also that there is some initial concentration of carbon dioxide in the gaseous phase. So we have three particular variables here, not variables, inputs here, I guess. So PCO2 is your partial pressure of carbon dioxide initially, right? So these are the three aspects we have, and obviously now what else are we missing? We are also missing sodium, right? And this more or less, as you see, are the list of or the species that we just listed, right? How many do we have? We have 6 species. They are more or less similar, not more or less, they are similar to what we listed in our closed system. But obviously now this is an open system, and which of these species or you are now going to have a new species, carbon dioxide in the gaseous phase, that is going to be in equilibrium with your H2CO3. So now we are going to list carbon dioxide, and this is the one in the gaseous phase, right? So this is your new species here. And so obviously again components. So we are going to again choose H plus and CO3 2 minus and Na plus, and let's see if we can get to or form all our species with these 3 components. So I guess the only new species that we need to look at is carbon dioxide. So let's do a check with respect to that first, and then move on to writing the other equations. So here what am I trying to form here? I am trying to form CO2, right, and it should more or less be 2H plus plus CO3 2 minus minus H2O should be equal to CO2, and these are my formation equations, right. So more or less 2H here, and I am going to subtract that here, and CO2 or H2O, CO3 2 minus, right. Yeah, now that is fine. So we have 2H plus plus CO3 2 minus minus 2H2O, and we now are able to use or use the building blocks of H and CO3 total and be able to form CO2. So we do not need any other or additional component to be able to form our new species, which is carbon dioxide. So now we can move on, and we will just list all the other species: H2CO3, HCO3 minus, CO3 2 minus, OH minus, H plus and Na plus. So we are going to put down what we looked at in the last example, I guess, and it is going to be again 2H plus plus CO3 2 minus, right, same case here, and again HCO3 minus, H plus and 1 CO3 2 minus, and here it is going to be only CO3 2 minus, and here it is going to be H2O minus H plus, and here it is going to be H plus and Na plus. So we will move on to writing our tableau: H plus, CO3 2 minus and Na plus. Let us go from easier to the more complex species: Na plus, H plus, OH minus, CO3 2 minus, HCO3 minus, H2CO3, and what else are we missing here? 1, 2, 3, 4, 5, 6, and obviously carbon dioxide. And then the recipe species, what are they? NaHCO3 naught, Na2CO3 naught, and partial pressure or carbon dioxide in the gaseous phase initially, right. So this is what we have, and so let us plug them in, and here it is going to be 1 and 1, 2, 3, 4, 5, 6, and the contribution here should be 1, 2 and 0, and similarly we are going to write down H first or H total, and no contribution here, 1, minus 1, 0, 1, 2, and for carbon dioxide we see that we need 2 again, right, and that is from this particular equation. So CO3 total, again 0 here, 0 here, 0 here, 1, 1, 1 and again 1, and where do we get this 1 from? From this particular equation here, right. And so moving on to the recipe species, again it is going to be 1, 1 and 1, right, and here it is going to be 1, 0, and here it is going to be 2, right, And so now we are done with our tableau, right, and the key here that we need to look at is with respect to jotting down your H total with respect to your carbon dioxide. Here you have a new species, the carbon dioxide in the gaseous phase, and that is something you need to take care of, right. So we will move on to the next crucial aspect, right. In general we just write down H total, and we are going to write that down something and so on, and we say that is going to be equal to a constant, right. So our whole setup or approach is based on component balance, or that the total component does never changes. But here the issue is that, let us say, depending on the initial concentrations of carbon dioxide in the aqueous and gaseous phases, right, it as in carbon dioxide can move from either gaseous to aqueous or aqueous to gaseous. Thus, if you just look at the balance on your liquid or aqueous form or just the gaseous form, you are not going to be able to look at a conservative quantity, right. Again I am going to repeat myself. So here we are trying to look at component balance, right. What is that about now? You want to look at balancing a conservative quantity, something that changes or does not change with respect to your system here, right. And if you are looking at this particular open system and trying to balance the H total in just the liquid phase, let us say, right, or the aqueous phase, how is that going to be affected? Let us say, if any carbon dioxide in the gaseous phase dissolves into your aqueous phase, you are going to have the relevant increase in your H total, right, but that is not going to work, right. Why is that? Again H total needs to be conservative. So let us look at how to go about it. So the only key is that if you look at it holistically now, so the total initial H, right, or H total in both the liquid and the gaseous phases is going to be equal to the H total in both the liquid and gaseous phase after equilibrium. Let us see what we are talking about here. So let us say, this is my liquid or aqueous or water phase here, this is water, and this is my gaseous phase here, and this is the initial. So for example, if there is H total 1 here and H total 2 here, right, and what is the H total? That is going to be equal to HT1 plus HT2. This is initially now, but after equilibrium, let us say, after equilibrium has been achieved, let us say, right. So carbon dioxide can move from gaseous to aqueous or aqueous to gaseous. So now it is going to change. So now we are going to have HT3 and HT4 now, right. HT3 is the H total in the aqueous phase, HT4 is the H total in the gaseous phase, right. So this is after equilibrium now. So the H total here is going to be equal to HT3 plus HT4 now, right. So again the total number of moles are going to be constant, so obviously we need to look at the volume too. So the H total before and after your particular equilibrium is going to be the same, and so thus I guess here I assumed equal volumes. So we also need to take into account the relevant volumes of your gas and liquid, right, and that is the approach here. Again, what is the approach? The total H or the total component in both the gaseous and liquid phases before equilibrium is going to be the same as the total H or the total component H in the gaseous and aqueous phase after equilibrium. So that is something we are going to write down. So let us develop the generic case first, right. So we are going to look at different variables: volume of liquid, volume of gas, right, H total in the liquid phase initially, and H total in the liquid after equilibrium, and also H total in the gaseous phase initially, and also H total in the gaseous phase at equilibrium, right. So these are the different variables we are going to consider here. And now let us look at the balance here, and so the moles are H total initially, and I am going to try to represent that particular case here or this particular case now, and volume of the liquid into H total liquid initially plus volume of the gas into H total in the gaseous phase initially. So this is the initial condition that we just described now, right. So this is the total H in both the gaseous and aqueous forms, and what is that going to be equal to after equilibrium? More or less the relevant variables that we are going to list here, right. Volume of the liquid into H total of the liquid after equilibrium, right, plus volume of the gas into H total in the gaseous phase after equilibrium, right. So this is what we have. So again we have a component balance, so but we are taking into account that the system is an open system, as in there can be a transfer of your particular H total between the gaseous and aqueous phase, either from the gas to aqueous or aqueous to gaseous phase. Again, think of this now, H can either move from H2CO3 to HCO3 minus. Similarly, think of it as it can move from the gaseous to the aqueous phase. So, that is the same case here. We are taking that particular transformation into account here. So, we need to obviously simplify this further. Let us go ahead. So, I am more or less interested in H total here in this case. So, I am going to have that term here, VL into H total of H total in the aqueous phase at equilibrium is going to be equal to VL into H total in the aqueous phase initially plus volume of the gas into H total in the gaseous phase initially minus H total in the gaseous phase at equilibrium, right. So, what does this mean now? So, the H at equilibrium in the aqueous phase is going to be that present initially and the change between the H total in the gaseous phase. So, again let us try to understand what we just looked at here. We are trying to look at H total in the liquid phase after equilibrium will obviously be equal to the H total in the liquid phase initially plus the change from gas to liquid that we are going to observe. Let us say it can either be positive or negative, right. So, let us try to simplify this though. So, H total in the liquid phase is going to be equal to H total in the liquid phase at or initially plus volume of the gas by volume of the liquid into the change in H total in the gaseous phase initially and finally. So, for ease of use and understanding, I am going to write it in terms of a particular variable and I am going to express this particular set of variable as that is going to be equal to delta or plus delta H total, right, change from gas to liquid phase, I guess, right. I am just approximating this, not approximating, I guess, using a different nomenclature, so that whenever I mention H total is going to be H total gas to liquid, right. This is a term that I am going to use for my particular ease of understanding, I guess. And what is this giving me an idea about? It is giving me an idea about the change in H from the gaseous to the liquid phase per unit volume of the liquid, right. So, that is what we have here. So, keep this in mind. Let us again try to understand this. So, we just looked at that, I guess, delta H T from gaseous to liquid is going to be equal to V G by V L into H total initial in the gaseous phase, right. Is it the initial? Yes, minus H total in the gaseous phase at equilibrium, right. Again, this gives you an idea about H T change in the gaseous phase to the liquid phase, right. So, that is what we have here. So, let us understand this, I guess, in terms of what we looked at. So, in general we are looking at carbon dioxide equilibrium between the gaseous and aqueous phase. Let us look at that relevant formation equation, right. So, in general we have 2H plus CO3 2 minus H2O is equal to your CO2, right, and this is your formation equation that we listed previously, right. So, let us try to understand the change in terms of these variables now, right. So, the delta H total from gas to liquid is going to be equal to 2 times the change in any carbon dioxide total from gas to liquid, right. So, whenever there is change in 1 mole of, let us say, carbon dioxide, there is going to be effect of 2 moles on H plus. So, that is what we are talking about here, and same case here, delta CO3 total gas to liquid is going to be equal to 1 times delta CO2 total gas to liquid, right. So, more or less both these equations are from this particular equation here, yes. And we are now going to take this further again, similar to what we discussed in the previous session, and let us see what we had there. And I believe we can always express delta CO2 total from gas to liquid in terms of partial pressure of CO2, but we are going to look at that later on, right. anyhow, where do we have here, or let us get this done here. That is going to be equal to CO2 total initially in the gaseous phase minus CO2 total initially, not initially, pardon me, at equilibrium in the gaseous phase into Vg by Vl, right. And so I can express this as Vg by Vl into, looking at PV equal to nRT. What is this going to be equal to? This is going to be partial pressure of CO2 initially by RT minus partial pressure of CO2 at equilibrium by RT. And where is this from again? We have PV equal to nRT, or ideal gas law, right. And so your N by V, which is your concentration here, is going to be equal to P by RT, and that is what we have here. So that is going to be Vg by Vl into RT into initial partial pressure minus the equilibrium partial pressure, right. Anyway, this is something I believe we are going to use later on down the line, right. So let us move further. So we have our H total, let us say, and what is that equal to now? This is H total in the liquid phase is going to be equal to concentration of H plus minus concentration of OH minus plus 2 times the concentration of H2CO3, right, plus 1 times the concentration of HCO3 minus. Let us look at the tableau once, and that is what we see here, 1, 2, 3, 4, and obviously carbon dioxide, but here we are only looking at the liquid phase, so we are going to omit carbon dioxide here for now, right. But obviously what is this going to be equal to now? This, as we know, is going to be equal to HTL is going to be the one initially plus any change from the gas to liquid, right, and that is what we have here. Yes, and that is what we looked at here. And that is going to be equal to your concentration of H plus minus Kw by concentration of H plus plus 2 times the concentration of H2CO3 plus 1 times the concentration of HCO3 minus, right. So again, let us try to simplify the particular equation, right. Here we have we still have multiple unknowns in this particular equation, so we need to be able to simplify it to such an extent that we only have a couple of variables here, right. And let us look at that. So first we are going to simplify H2CO3 and HCO3 minus, and how do we do that? We know that CO3 total in the liquid phase anyway, again keep in mind that we are doing the balance only on the liquid phase here, is going to be equal to H2CO3 plus HCO3 minus plus CO3 2 minus. This is from your particular component balance, right. And let us move on to the next slide. And so thus H2CO3, and also considering your equilibrium particular values, what will they be equal to now? It will be equal to alpha naught, or what is alpha naught now? H2CO3 by CO3 total. So thus you are going to have CO3 H2CO3 equal to alpha naught into CO3 total, right. So let us have that here though, H2CO3 is equal to alpha naught into CO3 total. So the key here is that, you know, this is something similar to what we looked at earlier. So let us simplify that and also come back to what I am trying to draw you towards, is going to be equal to alpha 1 into CO3 total, and I am going to plug this in the previous equation, and what is that going to be equal to? So the H total liquid phase is going to be equal to H plus minus Kw by concentration of H plus, right, plus 2 times alpha naught plus alpha 1 into CO3 total, right. Is that true here? And where do we have that, please? 2 times alpha naught plus alpha 1 into CO3 total, right. But here the key is that we can never depend upon CO3 total in the liquid phase. Why is that? That can change whenever there is transformation of carbon dioxide from the gaseous to the aqueous phase, right. So here we are going to look at variables, or how to connect, or connect the dots between CO3 total and partial pressure of your carbon dioxide. Let us look at that now. So you now have your Henry's constant, right, and you know that it will give an idea about the concentration in the gaseous phase to the concentration in the aqueous phase, right. And again we talked about this, that the units can be you know, there are different kinds of constants depending on the units. So you can even define H, let us say I will call that KH now though, as the aqueous concentration by the gaseous concentration. As in, again keep in mind that still Henry's constant, but depends on the units. You can either have the numerator and denominator above, or you know, the vice versa, right. So again this is what we are going to use now for purposes of simplicity, right. The Henry's constant is going to be equal to concentration in the aqueous phase, right, CO2 in the aqueous phase by concentration in the gaseous phase is going to be equal to PCO2, and we know that this is going to be equal to H2CO3 concentration by PCO2. And what does that mean? Henry's constant, or KH, written in the form of aqueous by gaseous. Keep in mind that we are defining KH as aqueous by gaseous concentrations, is going to be equal to alpha naught, and this is from here again this equation, alpha naught into CO3 total in the liquid by partial pressure of CO2, right. So what is the take home message here? That CO3 total in the liquid phase is going to be equal to KH into PCO2 by alpha naught, and I am going to plug this in this particular equation, and thus I am going to end up with H total in the liquid phase is going to be equal to H plus minus KW by H plus 2 times alpha naught plus alpha 1 into CO3 total in the liquid phase. Am I done with it now? I mean, pardon me, I guess I still obviously need to plug that in, right, the relevant equation that we just derived, KH into PCO2 by alpha naught, right. So again, what are we trying to do here? We are trying to express the variables in terms of the relevant what do we say, variables you would come across in an open system, right. So instead of using CO3 total would be relevant if it is only a closed system, but if it is open to the atmosphere, right, you are concerned with the partial pressure of carbon dioxide, or which more or less means the carbon dioxide concentration in the gaseous phase. So thus we have been trying, or we tried to, and were successful in expressing CO3 total in terms of the partial pressure of carbon dioxide that is going to be at equilibrium. Keep in mind that these are the values at equilibrium, right. So are we done here though? Not yet. Why is that? We still have H total liquid is H total liquid initial, which is what you know, right. This is what you know, you always know the initial concentrations, plus delta H total liquid to gas, or gas to liquid, right. This is the change that you are aware of. So we still need to be able to figure out how to express this particular variable, or change in your particular H total from gas to liquid in here, right. So that is what we are going to do here. And what is that going to be equal to, and where is this equation from? This is from more or less this particular mass balance, right. You have that particular mass balance there. So let us try to come back to here and let us try to see that. So that is going to be equal to H total initially in the liquid phase plus 2 times delta CO2 gas to liquid, right. And this is something again we looked at earlier. We saw that for every mole of CO2, or for one component of CO2, let us say, or one species of CO2 that is going to change from gas to liquid, we have a component of H plus 2 change, I guess, right. So that is what we have here, and then we are going to express in terms that we know, that is again going to be H total in the liquid plus 2 times delta CO3 total gas to liquid, right. So continuing from our previous slide, right, H total L at equilibrium is going to be equal to H total in the aqueous solution initially plus 2 times the change in CO3 total from gas to liquid, right. And let us try to simplify this further. We know that CO3 total in the liquid phase at equilibrium is going to be equal to CO3 total in the liquid phase initially, again this is initial, so we know what this particular value is, plus the change in CO3 total from gas to liquid. Again this is similar to what we derived earlier with respect to H total liquid is going to be equal to H total initially in the liquid plus delta H total change from gas to liquid, right, more or less the same here. So now we have this particular variable, and so continuing from here, delta CO3 total gas to liquid is going to be equal to CO3 total in the aqueous phase at equilibrium minus CO3 total initially in the aqueous phase. So I am going to plug this in here, that is going to be equal to H total initially in the liquid phase, which is something that you know, it's right, you know what it is you are putting in initially in your water, and that is going to be equal to 2 times CO3 total liquid or at equilibrium minus CO3 total initially in the aqueous phase. Again that is going to be equal to H total initial in the aqueous phase plus 2 times, and how did we express this as pH, kH into PCO2 by alpha naught minus CO3 total initially at equilibrium, not equilibrium, pardon me, initially in your aqueous phase. Let me check this variable. When we have that, CO3 total is going to be equal to kH into PCO2 by alpha naught, and that's something we have. And so this, as we know, is now equal to concentration of H plus minus Kw by concentration of H plus 2 times alpha naught plus alpha 1 into kH PCO2 at equilibrium by alpha naught, right. So this is equal to this, and this is a variable that you know, this is equal to the H total initially, so that is something that you know, and this particular variable CO3 total initially at or in the aqueous phase is something that you know how much you are putting in into your system, and H plus is the H plus concentration at equilibrium, PCO2 is the concentration of carbon dioxide in the gaseous phase at equilibrium, and thus let us say we can identify the relevant variables. What are they here? They are going to be pH, H total and partial pressure of CO2 though. This is the one in open system, but what was it in closed system? It was pH, H total and CO3 total, and this was in a closed system, right. So again earlier in the closed system the relevant variables were pH, H total and CO3 total, H total and CO3 total that were present or that are going to be present at equilibrium. But in this case though we have a slight variation. Why is that? It is no more a closed system, it is an open system, right. So thus the CO3 or H2CO3 is going to be in equilibrium with CO2 in the gaseous phase, right. So now the relevant variables are pH, H total and partial pressure of carbon dioxide in the gaseous phase, right. So in the next class or next lecture session anyway, we are going to look at the applications of Vimentech with respect to the open systems, and then we are going to move on to titrations and so on. And I guess with that I will be done for today's lecture session, and thank you.